Hi, science kids. So we've been talking about sound and light and things that travel in waves. Now we're going to completely switch that up and talk about things that are a bit more closely associated with our usual definition of energy. When we mention energy, we tend to think of things like lightning bolts or plugging in our electronics or light bulbs and stuff like that, and that all comes down to electricity. So this is 6.6 about electricity. We're going to be talking about the basics of electricity today. Then next week we'll talk a little bit about circuits and how circuits works, and then we'll wrap the unit up by talking about magnetism. And so we're getting close to the end of this unit. Somehow. It seems like we just started this unit. Okay, so moving on. So what is electricity anyway? Electricity is change in electrical charge, which is carried by electrons. You remember electrons are subatomic particles. They're found on the outside edges of our atoms. Electrons can be gained or lost from atoms relatively easily, and so there's just tons of electrons around. They're in everything, so most anything is potentially have electrical charge. And then we can move them around fairly easily because they're not very strongly attached to atoms a lot of the time. So when you gain electrons, you end up with an overall negative charge, and if you lose electrons, you end up with a positive charge. These act a lot like magnetic charges in that if you try to push two negatively charged objects together, they'll repel each other, or two positively objects. So like charges repel, and opposite charges attract. And so you end up with negative and a positive one, they stick together like magnets. And what electricity actually is sort of like a dominoes effect. You're not trying to take like a single electron and thread it all the way down the wire to get it to your light bulb. That would take forever. Instead, you add one electron to the far end of the light bulb, and a different electron pops out this side, and you've triggered like a cascade of electrons bumping into each other until a different one pops out. So electricity is a lot more like dominoes than like an individual electron getting all the way from the power plant to your light bulb. That would take ages. Okay, so how do we generate electricity? Well, there's a couple different ways. We use batteries a lot of the time, things like AA's or AAA's, or your cell phones run on batteries. Batteries work by converting chemical energy into electrical energy. The type of chemical reaction that's involved varies a bit. You've probably heard about lithium-ion batteries, maybe. That would be a specific chemical reaction. But one thing that's true about batteries is these chemical reactions don't last forever. Some batteries are rechargeable, like our cell phone batteries are, but even then there's a limited number of times that they can take that recharge, and eventually the batteries wear out. And so batteries are always sort of temporary. And honestly, battery technology is not as good as we would hope. We've come up with really big advances in the last 20 years or so, like the way that our cell phone batteries last much longer than anything we would have had in the 90s. But like if we're trying to run a house off a solar panel, stuff like that, having batteries that can hold enough energy long enough to run houses or entire buildings is still a major problem. And it's one of the things that is tricky about using renewable resources like sunlight, because they're not available necessarily every day or all day, or wind power is not every day, all day. And so trying to maintain a consistent flow requires good batteries. And so there's still a lot of advances that we require in battery technology in order to really effectively generate power from a lot of different sources. Anyway, there's lots of cool stuff going on there. That's kind of a little hobby horse of mine. But anyway, the second way, the way that our power plants work is through generators. You also might have a generator at your house sometimes. It works more or less the same way. There's something that's being burnt to turn a turbine. With a generator at your house, it would be gasoline that you put into it, and then it makes things spin, and that generates electricity. But it's converting the mechanical energy of that spin into electrical energy. Usually it involves steam, because steam's an easy way to turn things. You can heat water, and it makes steam, and the steam pushes against the blades of the turbine, and then it just keeps making it spin, and then it makes magnets rotate, and then you get electricity. So, depends on how we do it. Most of our power plants use it that way, either by burning coal, or even nuclear power plants still use it to heat up water to make steam. It's like we use this very fancy, complex way to make heat, and then we do this very old-fashioned thing to make steam. But it's an interesting little comparison there. Okay, and then, or you can just use falling water to make the turbines move. That would be like a hydroelectric dam. And like geothermal energy too. There's a couple other ones, but those are the two big ones. Okay, so we're making electrical currents. There's two different types of currents based on which way we're trying to make them go. There's direct current, where we just push the electrons just one way all the time. This is how batteries work. That's why they have a positive and a negative terminus. And if you put the batteries in the wrong way, it doesn't work anymore. Then there's also alternating current, where instead of trying to push the electrons all in the same direction, which is like I said, it's like shoving dominoes, and the dominoes aren't necessarily resetting themselves very well. We're having the electrons go back and forth. And so instead of having the dominoes fall all the way over, we're just making them rock back and forth, I guess, is the way to think of it. So they keep nudging their neighbors and passing on the energy, but they keep returning to their own stable state, too. So alternating current is more like vibration. And this is how our houses work. The power lines are carrying the alternating current. When you plug anything into the wall, that's using AC. And so often, it's either or. It either runs on batteries or through alternating current. Trying to come up with batteries that you can charge up with alternating current was a big deal. So that's why rechargeable batteries are still more expensive than normal batteries. And are actually a fairly new form of technology. Okay, so what are the main properties of electricity? Electricity has a current, which is the rate at which electrons move. We're going to give current the letter I in our formula. And the unit for current is amperes, which is in capital A. Then electricity also has voltage. You've probably heard of voltage. This is basically how much change there is in the electrical potential energy of the electrons. This is a lot like gravitational potential energy. Remember, we talked a lot about falling down the stairs. When you're climbing up the stairs, you're storing up more gravitational potential energy. Electrical potential energy is the same thing, except it's about how much the electrons want to move because of the electrical field that they're in. They're being attracted to the opposite side, the positive pole, and they want to move that direction, but maybe they can't because, because of what they're mixed in with or the material they're a part of or whatever. And so it's measuring the strength of the tug. How quickly do the electrons want to move, even if they're not moving yet. Anyway, voltage is easy because it's capital V for voltage, and it's measured in volts, which is also capital V. And so very easy to keep track of. And then resistance. Resistance is opposition to motion. It's kind of like friction for electrons. The more resistance you have, the slower the electrons can move through the material, and the more stuff is lost as heat as well. So it's measured in ohms, which is the scientist's name, of course, who discovered this. And it's given the Greek letter omega here as its symbol. So, and then in the formula, the letter for resistance is just capital R, so that's easy to remember. Okay, so the relationship between these three is known as Ohm's law, based on, again, on that scientist, where the voltage is equal to the current times the resistance. Where voltage is in volts, current is in amps, and resistance is in ohms. And so if we're solving it for V, V is just I times R. If we're solving it for I, for the current is V divided by R, voltage divided by resistance. And if we're solving it for the resistance, it's the voltage divided by the current. So pretty easy. So here's an example. What is the resistance in a circuit with 4 amps of current running on a 9-volt battery? So I list my variables. The current is 4 amps, and the voltage is 9 volts. I'm being asked to find R, so R equals V divided by I, so 9 volts divided by 4 amps, 2.25 ohms. And it's done. These are pretty easy. So you are going to be doing math on this homework assignment, but it is very easy math. So hopefully this won't be too shocking for you. On the homework, we're not putting in units, just numbers, and remember to round to 2 decimal places because the Google Forms I've been using are not good at picking up subtle differences. And so it was having a lot of trouble reading people's answers as correct because they had a space between or didn't have a space between their number and the unit and stuff like that. So no units at all, just numbers, 2 decimal places. And that should be easy enough. Okay, have a great day, and tomorrow you'll have a quiz on Friday, and then have a great weekend.